Hi everyone, hope you're all keeping well, keeping yourselves safe during these difficult times. It's now time for our next lesson. Today it will be our final, actually our final instalment from the current unit. We've been looking at waves of radiation. So the last part of the radiation radioactivity that we're looking at now. We're going to be looking at nuclear reactions, okay? So learning intention to explore different types of nuclear reactions and to examine the pros and cons, advantages and disadvantages of nuclear reactors in electricity generation. And hopefully by the end of the lesson you'll be able to name the two types of nuclear reaction that we're going to be discussing today. You will be able to describe how energy is released during each of these nuclear reactions, and you'll be able to state the advantages and disadvantages then of electricity generation from nuclear power stations using nuclear energy. Now, just to start off with, just before going to the next slide, there's a couple of things I'm also going to throw in here that I've not covered in any of the previous lessons that we just need to kind of cover. So just a couple of little bits just to start off with, just to kind of tidy up what we've kind of looked at in the past. Okay, so the first of those is ionisation. Now, I'm just going to go through these really quickly. So ionisation is basically just where an atom loses or gains an electron. And those of you that do chemistry may have came across this already, in which case that's absolutely great. Just listen in, I'm going to tell you exactly what you need to know about ionisation in terms of physics. I'm not entirely sure what you need to know in terms of the chemistry behind it when you're looking at chemistry. But for physics, this is exactly what you need to know. So ionisation is where an atom loses or gains an electron. Now, obviously, if it loses an electron, it's going to have one less electron or more than one less electron than it had to start with. And because the nucleus is positively charged and balances out the charge of the electrons surrounding the nucleus, if it's got less electrons surrounding that nucleus, then we end up with it being positively charged. So if it loses electrons, the atom becomes positively charged. And if the atom gains electrons, so it's then got extra electrons in this cloud orbiting the nucleus, still got the same number of protons, so there's still the same amount of charge in the centre, there's just more charge around about the outside, more negative charge around about the outside, which means it's going to become negatively charged. And once an atom becomes ionised like that, we tend to call it an ion. It either has a positive or a negative charge. This is important because when an atom interacts with nuclear radiation, it can become ionised. So if you think of an alpha particle, remember back to when we looked at alpha particles, if you've got an alpha particle that goes blundering into an atom and next two of its electrons, for instance, or one of its electrons, that atom that is going to go and blundered into is now going to have less electrons. And if it's got less electrons, it's became positively charged. That's a problem. If you've got a beta particle and it interacts with an atom, that atom's going to gain an electron in its cloud of electrons that are orbiting it, and it's going to become negatively charged. Again, this can be a problem, and this is what can actually cause mutations when you look at when you're looking at kind of how radioactivity interacts with the biology, with kind of living things. So if you've got atoms which have gained or lost electrons, it doesn't take an awful lot of electrons to have been gained or lost for DNA to be compromised and for mutations to be introduced. The DNA can be very, very sensitive to these kind of changes. At that point, I'm going to leave it at that. I don't want to talk too much about mutations and the kind of biology of the situation. We'll leave that for the biologists. However, I just wanted to make sure we kind of covered that first thing here. Now, one other thing I want to cover, that is radiation safety. This isn't something we've looked at previously either, and it's just something that's really, really important, that we know how to keep ourselves safe if we were working with radiation. This is normally something I would do in class when we were actually looking at radioactive sources. Now we'll be kind of demonstrating a lot of these things as we kind of went along. So that's kind of why we've not kind of really covered it as part of an individual lesson at this point in time. So a number of things, I'm just going to run through them really quickly here. So the first one here, we would always use tongs to handle radioactive sources. We're not going to handle them directly with our hands. You wouldn't even want to really put gloves on. You want to try and keep your distance as far as possible. You don't want to be touching any of the apparatus really that's kind of surrounding that radioactive source. So always use tongs. So you're keeping yourself safe, you're keeping yourself from touching it. Make sure that the source always points away from you. Now, when we work with them in school, what we do is they're actually housed in a little container, so that the radioactive source is always going to be pointing just in one direction, and that way we can make sure that it doesn't point towards either myself or you or anyone else that it could be pointing towards. Now, obviously, if you are working in the radiation industry, you're going to have to get it into these kind of containers, so this might not always be possible, but ideally you do want to be making sure that you're pointing your source away from any kind of living material wherever possible. Always store your sources in a lead-lined box. Now, you remember that we talked about the different things that we need to stop different types of material. If you've got it in a lead-lined box, then that's going to be stopping most of the gamma rays from escaping. The alpha particles aren't going to get through lead because it's only paper. We need to stop them. The beta particles, we only need aluminium, so the lead will stop them as well. So the lead's going to stop or prevent most of the gamma radiation getting out as well. So it's going to keep us as safe as possible. Label everything. So label your radioactive source. What's the point in having it in a nice, safe, lead-lined box if nobody knows what's in it? I mean, if I don't know what's in a box and I go, oh, I wonder what's in this box, open it up, pick it up, go, oh, I probably should be touching that. That's a problem. I'll put it back. I'm not going to touch that. If it's labelled, I know I'm not going to touch that without the correct safety precautions in place. Limit the time of exposure. So, you know, if I'm working with radiation, work with it for a short space of time. If I limit the time as much as possible, then that's going to keep me as safe as possible. So I don't want to be working with it for any longer than I absolutely have to. Increase your distance from the radioactive source. So if the radioactive source is on one side of the room and I can be in the other side of the room, that's the best place for me to be. If I can be in a different room, even better, although obviously you want to make sure that there's no one else who's going to be interfering or putting themselves in harm's way when it comes to your radioactive sources. Monitor your exposure. You'll remember back to one of the lessons I did previously, we talked about the little film badges. That's one of the ways that we can monitor exposure. There's lots of different ways. So I'll not talk too much about that, but you can kind of use these little badges to monitor exposure. If you're unsure what I'm talking about, go back and watch I think it was the last video I did where we talked a little bit about measuring or ways of detecting radiation, nuclear radiation. One of the other things I should say that I haven't put in this list here, maybe I'll add it in just before I can actually create the video. You can obviously wear protective clothing, so you could wear protective gloves, you can wear a radiation suit, for instance. These would all be ways of keeping yourself safe as well. If you are in a hospital, for instance, quite often they will have kind of a lead-lined vests, for instance, which will help to protect people that are working with radiation. When it's been used for cancer patients to help to limit their exposure, particularly their vital organs, which are the most susceptible parts of the body to the nuclear radiation, to be damaged and cause mutations by the nuclear radiation. So that's just the two wee things I wanted to kind of cover, just that we hadn't covered elsewhere. I just wanted to make sure that we'd covered them so that we were all quite clear on them. So if we now get into what the focus of today's lesson is, the first type of nuclear reaction that we want to talk about is nuclear fission. Okay, so nuclear fission is where we have a large atom. It can be a large unstable atom. The larger the atom is, the more unstable it tends to be. So it tends to be a large unstable atom, and it splits into two smaller atoms. So we've got a large, we tend to just concentrate on the nucleus, because the nucleus is kind of where all the kind of important things are happening here. So we've got a large nucleus here, and essentially this nucleus splits into two, and that we end up with two smaller atoms. Now, what we can do is we can actually cause this to happen artificially. So what we do is we get a little neutron. Now, just to remind you, I've kind of kept the same kind of colours as I did in the previous video. So we've got the red are the protons here, and the blue are the neutrons. So what I do is I get a little neutron, and I just fire it at the nucleus. It's absorbed by the nucleus, and it makes it unstable if it isn't already unstable, or it makes it more unstable, and it tends to cause it to undergo a nuclear fission reaction fairly quickly. So if I fire that in there, the atom splits into two smaller atoms. You also find that you'll have some neutrons given off as well. Now these neutrons can be quite useful, although they can also be quite dangerous. You'll notice there's now 3 neutrons in this have been emitted during this reaction. Now they are now free to go and interact with another atom, and they can cause exactly the same thing, except we've now got 3 neutrons, so that's 3 atoms. Okay, so from one nuclear reaction we could now have 3 nuclear reactions happening. That actually is what we call a chain reaction. You'll have heard of the term undoubtedly chain reaction, and if this is kind of kept unchecked, if we just have each of those 3 atoms disintegrating and releasing another 3, then that's 9 that we're going to have. 9 neutrons released and able to interact with 9 nuclei, and kind of so on and so forth, and it kind of escalates very, very, very quickly. So that's why we need to be very, very careful with a nuclear fission reaction. We use these, and it's actually nuclear fission that we use in nuclear reactors. What they do is they have what's called control rods, and you may have heard of them before. What the control rods do is they absorb some of these neutrons that are emitted here. So it would maybe absorb 2 of these, and you'd be left with 1 which is able to go and interact with another atom, and you're able to control your reaction that way. So just a wee aside here, during this process some energy is released, and this is really, really important actually, because if there weren't any energy released, it wouldn't be useful in electricity generation. So during the process, during this nuclear fission process, we have some energy release, and this is harnessed in nuclear power stations and converted into electrical energy. We'll have a little look at how that kind of a process happens in the next unit when we're looking at electricity. We'll have a look at electricity generation in that unit. So I'm not going to talk about how that energy is harnessed. We'll look at that at a later stage. But we can harness that energy in a nuclear power station, and that's exactly how we are able to generate electricity there. So the second type of nuclear reaction we want to be looking at is nuclear fusion. So nuclear fusion is where we have 2 smaller atoms this time, and what we do is they are fused together against the nuclei we're looking at here. These 2 nuclei are fused together or joined together, and they make one bigger atom. So we start off with 2 smaller nuclei here. So we have an atom with 1 proton and 1 neutron, and here we've got 1 proton and 2 neutrons. So these are going to be 2 different types of hydrogen atom. For those of you that do chemistry, I'm sure you've already figured that out already. And what we're going to do is we're going to just fire them at each other, and we have this explosion there, and we end up with 1 larger atom here, and we end up with a wee extra neutron that's kind of shoots off in that direction. Now, like our previous reaction, we get energy released during this process. A lot of energy, I have to say, and this is exactly how the sun actually produces its energy. And this is a type of nuclear reaction that is undergone on the surface of the sun. It's nuclear fusion reactions that excuse me, that the sun is undergoing. The scientists are currently trying to harness this kind of type of electricity or energy generation and use it in electricity generation. Now, we're still, as far as I'm aware, still quite a wee while away. They've been working on this for a long time. They're very excited, and the work happens in the UK with regards to this. There's work all over Europe and kind of throughout the world, because you can get huge amounts of energy from nuclear fusion, much more actually than you can get from nuclear fission. And actually it's much cleaner as well. That's the real benefit of nuclear fusion. You don't tend to have the same radioactive waste to deal with. You might have a little bit of radioactive waste, but it doesn't tend to, as far as I'm aware, be radioactive for anywhere near as long as the waste products that you get from a nuclear fission reaction. So that's the 2 types of nuclear reaction that we need to talk about. So nuclear power and electricity generation from nuclear power now. As I've already said, so current nuclear reactors use nuclear fission in order to generate electricity. Loads of pros, loads of cons for it. That's what we're going to look at here. We're going to look at what the advantages are of that, what the disadvantages are of that. Ideally, we would be moving to nuclear fusion, which is brilliant because, as I say, very little, if any, radioactive waste. It's much cleaner, but the technology is just not there yet. So maybe at some point in the future, maybe one of you will be the one to solve that problem. Who knows? But at the moment, what they can do, they can actually do nuclear fusion reactions. They can fuse nuclei together. However, it takes more energy. You're having to put more energy into the system than you're getting out, and ultimately it just isn't feasible from a financial point of view. It costs more basically to kind of fuse these atoms together than it would to you would be able to declaim from any electricity generated from it. So that's where the big issue is. So I'm just going to put this table up here. This is the advantages and the disadvantages. I'll read through them really quickly. I'll maybe make a couple of points as we go. I will put the PowerPoint obviously up on Google Classroom, so don't feel that you need to be trying to scribble this down as quickly as possible, having to pause it. You can pause it just now and obviously copy these down if you want, but I will have the PowerPoint up in Google Classroom as well, so you can see this. So the advantages of nuclear power. Well, first of all, it doesn't produce carbon dioxide like a fossil fuel power station. So obviously fossil fuel power stations like those that use coal, oil or gas, they release carbon dioxide into the atmosphere. They do use technology these days which tries to capture some, if not all of that carbon dioxide, but there's still lots of nasty things released during the burning of your fossil fuels. That doesn't happen during a nuclear fission reaction. So brilliant, no carbon dioxide, no sulfur dioxides or any of these things which can cause acid rain, things like that, all these pollutants, but none of these kind of things released into the atmosphere. It doesn't use fossil fuels, which of course are running out as well. Fossil fuels, by their very nature, are limited because they take thousands and thousands of years to be made. We don't have thousands and thousands of years in order to replenish them, so obviously we're burning through them much quicker than we would like. A small amount of this nuclear fuel goes a long way. You can get a huge amount of energy from a small amount of nuclear fuel. Even with a nuclear fission reaction, you get a lot, you can get a lot of energy out just from a small amount of nuclear fuel in one of these fission reactions. Even more, as I said, in a fusion reaction, but we're not kind of really discussing that just now. We'll just concentrate on fission. So a small amount of nuclear material, nuclear fuel, goes a long way. And finally, the waste products, it all stays in one place normally. I'll come back to the normally in a wee second, but normally it's not going to enter the atmosphere, so it's all kept in one place, so that makes it much easier to manage. You're not having to develop new ways of trying to capture things like carbon dioxide or any other pollutants that are given off during your fossil fuel, burning of your fossil fuel. It just is there, it's in the reactor, it's not going anywhere. So all you have to do then is extract that waste material at the end, and obviously you do that very carefully, and then you can have a deal with it very carefully. However, that leads us on to the disadvantage. Nuclear power, obviously, nuclear reactions produce radioactive waste. There's the waste products that we were just talking about. This has to be stored for many, many years, hundreds of years, if not thousands of years quite often, in order for it to become safe. That's obviously a long time, so you've got to be thinking far into the future when you're kind of thinking about how you're going to be disposing of your nuclear waste, or storing it actually, because what you just need to do is store it and make sure that you can keep it safe for as long as it takes for it to become safe. Accidents can happen, and this takes us back to the normally in this previous slide. So accidents can happen, and they can have very serious consequences for the environment and the surrounding area. If you look at things like Chernobyl or Fukushima, the kind of two accidents that have kind of happened that are kind of quite well known. Chernobyl was back in the 80s, so at least 30 years, well over 30 years now I should say, since that happened. And it's my understanding, if you were to go into the reactor that went into meltdown during the accident at Chernobyl, you've got minutes in there before you have to get back out, because there's still such a high level of radioactivity in there. It's still a very, very dangerous place. Much of the surrounding area still can't be lived in. So very, very dire consequences. And as I said, that was well over 30 years ago now. Fukushima happened much more recently. That was an accident in Japan. There was a tidal wave, caused some problems at a power station there. At the end of the reactor's life, it's obviously then got to be dismantled. First of all, you've got to get rid of that nuclear waste. There's potentially going to be parts in there that are radiated. I've got no idea how a nuclear reactor is dismantled. It's complicated, it's expensive, you've got to be very careful. Obviously, takes a lot of money to do that. So these are all disadvantages and advantages of nuclear power. Lots of advantages, lots of disadvantages. Is it the best way forward? Well, that's a debate, I think, for another time. In fact, actually, what I'll maybe do is ask you guys to have or try and answer that question for me as a little task today. Okay, so I'm going to leave it there. That's the end of the learning just now. There will be a little task, or there'll be a couple of wee tasks that I'd like you to have a go at on Google Classroom. So get yourselves onto, obviously you're on Google Classroom already, have a look at the instructions. The instructions will be there for the task that I want you to do. I'm going to get you to do a little bit of research. I'm going to get you to prepare some slides and Google Slides, and at the end of that I'm going to ask you, I'll ask you to answer that question that I've just asked there. Is nuclear power worth it? Okay. So I'll get you to do kind of a couple of different things. You'll have a look into electricity generation using nuclear fuels, and I'll get you to look at the accidents as well. I'm going to get you to pick one of these famous accidents. I don't like using that word, but the well-known accidents such as Chernobyl or Fukushima, and do a little bit of research into them, and just kind of weigh up the pros and cons on those kind of scales, and I'll get you to submit that just at the end of the lesson today. So just to recap then, just before I finish up here, success criteria. I can name 2 types of nuclear reaction. Hopefully you're there already, hopefully you've got that done. I can describe how energy is released during each nuclear reaction. Again, I'm hoping you've managed to kind of pick that out now. If you do feel, whenever we get to any of these success criteria, if I'm going over a success criteria and you're going, I'm not 100% sure about that, remember you can always rewind this video, go back to either to the start or just to the bit that you want to kind of revisit and look at that again. I can describe how energy is released during each nuclear reaction. I can state advantages and disadvantages of nuclear power and electricity generation via nuclear reactions. Okay, so again, we'll leave it at that. Have a look in the Google Classroom for specific instructions on what I want you to do. There will be a Google Slides document available on this this assignment in Google Classroom. So just do all your work in there. That makes it nice and easy because all the work will be in there. Then all you have to do is just submit that at the end of the period once you finish that. Okay, I'd like for that to ideally be finished by the end of today. Yeah, we'll go for the end of today's period. Okay, I'll leave it at that then, guys. See you later. Hopefully we'll get together soon. Obviously it's the middle of February now, we're at least until we're back in schools. We'll see what happens at that point in time. But until then, keep yourself safe, and see you later.